All right. So let's start. We have 30 minutes. I prepared 5 questions. Let me ask three and then open up to the floor. If we have time, we are gonna ask more questions. So for you, Dean and Anika, I wanna pick question one, three, and four among the list that I sent you. Um, Okay, so first question for me. As I presented in my own talk, we can learn a lot from the past experiences, right? And both of you have interesting experiences of flying real things to real space, and I suppose you learn a lot. So I wanna hear your stories, particularly if you guys had any interesting surprises. And if you did, how you guys handled, adapted to the new situations. Let's go first with Dean. I've heard interesting stories about Firefly pneumatic drills. So would you
Sure.
talk about it?
Yeah, so we had two payloads on Firefly's Blue Ghost Mission 1. Uh, the one in question was a pneumatic drill. It's called Lister. It's a 3 meter drill. It's a coil tubing drill, which means it's a stainless steel tube that's very stiff, and as you unwind it, it straightens. And then we use pneumatics to drill. So we're using pneumatics to blow regolith out of the hole, and then it's got a heat flow probe at the end, kind of a follow-on from the mole that Hiro showed. So when we were planning the mission, we chose a landing site that looked like it had no rocks, because obviously you don't really want to hit a rock with a system like this. So we chose one, it was nice and clean. Go there, we land. The lander doesn't land exactly where it's supposed to. One of the feet is kind of in a crater, so we're on the edge of a crater now. Um, Problem with the crater is it still looks nice from imagery, but below you'll have ejecta that then covered by softer regolith. So we go down 30 centimeters very easily. Everything's working great, and then we hit this ejector blanket, which is basically hitting gravel. And for a pneumatic system, gravel's not great because as you try and blow it out the hole, yeah, you blow it to the side, it doesn't all come out and then it kind of settles again. So it's really difficult to keep going. So, when I was talking adaptability and autonomy, that was a lot more, software related or hardware related adaptability. What we did here is more operational adaptability, where our team had planned for various circumstances and trained how to react in those cases. So this was, pretty close to as bad as it could have been, besides for like a big solid rock. So the team diligently worked at it and worked at it, and were able to get 1 meter below that gravels, which we counted as a huge success.
Can you share how you actually solved that rocket
It
issue you
was a
can
lot
share?
of hard work, a lot of sleepless nights, just
Yeah.
working at it, going little bits at a time. We just constantly were going, a couple millimeters at a time, and just back and forth. Kind of, you can't really retract this drill because it's a solid tube, but you could come back a little bit, and then blow a cavity to get the gravel out of the way. Come down, push as hard as you can without damaging the probe at the end, and then blow more out and kind
Okay.
of get down as much
Also
as you
manually
can.
commanding all
Manually commanding
the
up and
sequence
down.
of motions to go
Exactly.
through. Okay.
Yeah.
Awesome. Awesome. Cool. Let's go for Anika. Did you have any interesting stories like that from disarray tests in ISS or suborbital or parabolic flight tests?
Yeah, I mean, most of our lessons learned that I can think of are challenges we've had just with the test method itself. So we've had a lot of lessons learned, like from zero gravity flights, like you're not every parabola is going to be, a fully clean parabola. And so sometimes you go into it thinking you're going to get 20 seconds of clean microgravity, but it might be a pilot training day. And so suddenly you get sort of some wash and you end up with bad data. And so I think just building in contingencies to that kind of thing, like knowing that you're not going to have 30 good parabolas and being able to repeat some of your critical tests on those flights, just a lot of like kind of just experience from doing multiple of those. Knowing that someone might go down with nausea, and you're just gonna lose one of your people to a casualty of the zero gravity flight, then that's something we've had to learn a couple times. Having backups, we have a whole system down. Like we write our tests on our leg on tape. We all have our own systems for staying as not nauseous as possible. We have ginger gum. We have our own breakfast that we eat that we like sits well. Yeah, that kind of thing. I think we also learned a lot just from the ISS mission. I think maybe people here might some people might be familiar with ISS testing, but um, it's different if you go directly to uh, through ISS National Lab versus through a payload service provider. There's different speeds that you go depending on which route you go. Um, and so I think there's a lot of just trying to be a squeaky wheel, which unfortunately feels really uncomfortable, but just trying to be like, hey, we need to make a decision, otherwise, we're not gonna, make our launch. And so a lot of like operational, I think, lessons learned just from that standpoint of trying to get information early, understand the operating environment, limitations of testing in the vehicle with people with flammability risk. Uh, Basically make everything out of polycarb and metal and you'll be okay. But yeah.
Yeah, that's actually a interesting point because adaptation is not just about the your robot, but also your team has to adapt to new situations. So it's a reminder that we are not just flying robot; we are flying the team of robot and human on the ground. Awesome, awesome. Let's move on to question three, which I gave them beforehand. So, again, the theme of this session is how to design adaptivity instead of responding ad hoc with improvisation. So I wonder, if your system, either your drills or Annika's test array, have any designed features that are intended for dealing with unexpected situations. Dean, would you go first?
Sure. So, we try and design as much as we can for, hitting unknown unknowns, right? So, but, working on a private company budget is tough, especially these days where, everything needs to be cheaper and cheaper with this new paradigm of cheap commercial space. So, I like the examples you showed of, more degrees of freedom, more sensors, and reality of that is it's often hard to implement that because you're so budget constrained. So it's finding ways, clever ways of doing that and planning for contingencies. Um, for some of our R&D missions, it's a lot easier. Like the slush drill I showed, we can kind of do whatever we want. We can design in anything because it's R&D, so you can do anything cheap in R&D, and you can do all of these systems and sensors and spectrometers and lasers that make it full package Christmas tree, the thing that you can really detect anything and react to any situation. Conversely, when that gets to flight, then everything starts getting chopped out, and that's when it starts getting difficult. So a lot of the time, it will come down to operational adaptability, like I was talking about with the Lister drill, in which case that then you're putting your money into training people for reacting to certain circumstances. But as much as possible, you have your risks written down. You look at the worst ones, and you say, okay, well, we'll design to meet those ones. The ones lower down. If you hit a bad day,
Yeah,
it's going to happen. There's not much you can do about it.
great. Annika.
Yeah, I think there's kind of different levels of adaptivity, I think, in the test array system. So there's the idea that it is modular, at least more so than
Right.
we call the ISS modular, but really it's pretty permanent once those modules have come together. And those have been, maintained and replaced over time. But one aspect that we want to really build towards with test array is being able to replace tiles, right? And so say you want to go from one module to two modules, then you're able to add a berthing mechanism, which would then allow you building out a structure from just one module to multiple. Maybe you want a window somewhere, you add a window module, right? Or tile gets damaged, right? And so really trying to build out that capability is one aspect of our mission. At the kind of functional level for the current prototypes, I mentioned bad bonds, and so being able to adapt to the flight conditions is part of that. So being able to kind of respond to how they're coming together, and then use magnetic kind of throttling, we call it, to just basically like separate, come together better, inject a little bit more energy into the system. That's always been an aspect of that as well. And so, yeah, that's one element. I think the other one is just making the tiles smart enough to conserve their own energy when they are released sooner than others, because we do controlled releases. So having an understanding of how long they're going to be flying for, and making sure that that's taken into account when they're communicating, when they're, pulsing their magnets on and off, that kind of thing. Yeah.
You in your presentation you showed the soccer ball shaped structure, but can your tiles um, form different shapes, different 3D shapes in space?
Yeah, so the buckyball shape, like the soccer ball shape, that's really just like our ideal habitat use case, right? And so I think I mentioned this, but they can be that buckyball is achieved through beveling the edges. And so you can build out flat 2D structures. They again don't need to be pentagons and hexagons, they can all be hexagons. It's sort of just a matter of north-south magnet placements. And so yeah, it's shape agnostic. It's just a matter of what you want to build. And then building it into which face needs to come together to which.
Great. All right, let's move on to my final question, at least for now. You know, Annika and Dean represents commercial companies, which is very different from the conservative, super bureaucratic organization that I belong to. I should not say that. Is it recorded? Maybe so. It is. Anyways, so as I said, I partially argued that its rigidity partially comes from the requirement-based design approaches that NASA has been using for 60 years, and I'm wondering if you guys are innovative not just in technologies but also in the design process, because you're free from NASA, right? So um, if you have, perhaps I can broaden the scope, not just adaptivity, but any process improvement. But um, if your company has any interesting departure from conventional, space systems engineering process that you can share, I would love to learn from it. Dean?
Sure. So, not all that more flexible. We still have NASA as our customer for the
Weird
most
story
part.
about it.
And then we have our own people that we have to answer to. I talk about money a lot. I'm a BD person, so it always comes down to money. And NASA always gives us a certain amount, and then our people say, well, you can't spend more than this because we have to make some sort of profit. So we often get stuck between a rock and a hard place. So for us, recently it's been figuring out how to make things cheaper, which is good as a whole. And part of that comes in terms of process is, you know, traditional space, use space qualified pieces of hardware, very reliable, it's going to work because you can't go up and fix it, obviously. Whereas now, we're opening up the catalog a little bit. What else could we use? Can we get automotive parts and flight qualify them? How does lot qualification work when it comes to, one-off missions? Can we start moving in those directions? So, it's a lot. When you start moving away from NASA's way of doing it, the main thing is getting away from paperwork, because that's where a lot of the extra cost comes in, and doing all of this paperwork for Class A, Class B mission that becomes pretty burdensome. So what can we do to make sure our stuff is going to work? Because we still pride ourselves on everything that we've flown has worked. We don't have failures in space, while still being flexible to this new paradigm of the space industry.
Awesome. Annika, do you have something to share?
Yeah, I mean, I guess we're a little different because we're a nonprofit, right? So we're not, I guess, a traditional for-profit company.
Right.
But
You guys are even more free from NASA than Honeybee, right?
yeah, yeah, right, exactly. We do have a pretty scrappy team. We have like 2.5 people on our engineering team, and so I'd say like we're definitely not bogged down with systems engineering processes. We like we've taken material out and like lit it on fire outside in someone's backyard to see if it was a concern for flammability, and spoiler alert, it was. It lit on fire and it burned really well, so that was a sign we had to choose our material differently. Um, and I think on kind of I guess, a more broad level, we we're lucky in that we are residents of the Autodesk Technology Center in Boston. And so for those of you who aren't familiar, Autodesk makes a bunch of like software products, but they also have these design centers in different cities where they have residents who are working on different companies there. And so we sit next to people who are working on like new installation for buildings or like an automatic sale for basically like freight shipping. And so we have all these people doing crazy one-off projects. And so when we're trying to design, like for example, our dispenser, and maybe we're stuck on something or want to talk through like the best way to do something, we just go to people who are in that community, right? And so we're sourcing ideas from basically people who are doing other scrappy startup ideas. And so that's been really invaluable, I think, and kind of outside the mold a little bit for informing how we approach some problems and prototyping.
Yeah, and actually, Annika brought up a good point. It's something that we also do. Is a lot of the NASA process is you design to PDR, and it's a lot of paper design up to then, and you know very detailed paper design to make sure it's going to work. But what we find is our stuff has such complex interactions that we don't know for sure it's going to work. So we'll often rapid prototype quickly, throw it into a vacuum chamber, make sure it's going to work, and then iterate that way rather than just doing a design up to PDR. So by PDR, we've got a pretty well fleshed out prototype already. It's similar to how Annika's doing experiments beforehand to make sure you're choosing the right materials, you're choosing the right ways of doing things. That really speeds up the process and makes it more robust.
That reminds me of agile development,
Right.
which is typically employed in software companies. And we cannot introduce agile straight into flight yet, but we often use agile in research tasks at JPL. We are doing that in yields where, yes, scrap and build is the spirit. We prototype early and fail early and scrap early and, have a rapid pace adjustment. So, yeah, perhaps. And by the way, I'm not sure if it is published or not. Mars helicopter Ingenuity um, went through a quite different process, which is similar to scrap and build. Not precisely scrap and build, but which led to successful quick development.
Yeah, it
So
was they since they were a tech demo, they really took advantage of that to build this thing, and then only once it was on Mars and it worked really well did it become mission critical. So they kind of had the best of both
yeah,
worlds there, which worked out really well for the mission.
I believe there's a paper by both Barram if you are interested in that. Ask. Anyways, thank you very much, and I will open up to the floor for the remaining 15 minutes. Or a gentleman on the back with the glasses.
Okay, sure. So this question is for Dean, and so you're mentioning Honeybee responsible for Dragonfly, and software in particular, including the autonomy as well. So my question is, and for the autonomy, whether you can elaborate on the actual implementation approach. Do you use a rule-based, or you actually have some sort of machine learning and for autonomy?
No, for deep space missions, currently there's not a lot of like true autonomy or machine learning implemented because it's a much more sequential type of software programming. You want to make sure it's going to work. So, it's you send a command, it will go through its sequence, till the end, and then, ask the operator, am I good to move to the next step? So it's not true autonomy. The way that autonomy really comes in is, with fault detection. So if it sees, a high torque or a high load that it wasn't expecting, then we'll back off. That one's a smaller drill also, so much less likely to get stuck. So not, as autonomous as some of the other drills we're talking about.
But how do you address this problem with unknown environments, like how you do actual BNE for your software?
Yeah, that's where it gets tricky, and that's why autonomy is not commonly used in deep space missions, because the VNV is very difficult for that. To validate something that your machine learning algorithm is going to work every time exactly as you expected is really difficult to do, and so that becomes really expensive. So you usually do other things around it. When we're talking about these future autonomy things, that's 10, 20, 30 years in the future, so hopefully we'll figure some stuff out by then of how to do these things better. But for the moon it's a little bit easier. We can play around. Doesn't need to be fully verified. Class C-ish, class D tech demos, they don't need to be fully verified and validated. That you do have a little bit of freedom to fly some software. Even the Mars rovers, JPL still uploads software to the rover to date, so they can still do it. It's these deeper space missions that it becomes more difficult, especially if it's a short duration mission. So I don't think I gave you a good answer, but it's an answer.
Please.
So, with going back to the project management and the V and this sort of thing. So, personally, in my opinion, I could be wrong, but I see almost zero value in the normal design V for innovative work. I've never found value in a Gantt chart or anything like that, simply because you just have to change things so much. And
Yeah.
I've so I've been working with various universities, and in their senior capstone project, they're very rigid about this V, some of them. And it's like, from my perspective, it's like you say, they're kind of like holding themselves back because the ABET requirements don't require that, from what I can tell. And those students could get a lot more accomplished if they just meet the minimum paperwork requirements and not worry about that rigid V. And so maybe I'm wrong, but what would you communicate are the pluses and minuses to leaders of those programs of that kind of thinking? Like, is there something I missed? Because if it was up to me, I would tell them, don't do any of that. Just meet the minimum requirements for ABET and just program, design, build. That's it. Test. That's what I would tell them.
Annika, could you hear the question or not?
I think I heard most of it. Could you repeat? Yeah.
Yeah, gist of it is that, what's the pros and cons of using this V-shape systems engineering, and how, should we teach in schools, particularly for students?
Yeah, I'm a pretty big believer in like the project teaching, because I think in reality, and I don't know, I think there's formalities, at least when I was at NASA JPL, like there was very strict phases of the mission, right? And that's because you have to kind of align hundreds of people. But there's also some element of it that's like more of the spiral, right? And so you're going back to changing the design, you're making tweaks when you don't pass tests, or when something else, you get a budget cut, you get some other information. And so I think there's some element of just like teaching to that kind of flexibility based on challenges you encounter throughout the project is really important.
Yeah, process is developed from lessons learned, right? All of NASA process, they do it for a very specific reason, because they know if you follow the process, the thing you have at the end is going to work, right? But then what happens is, with this process comes a lot of making sure you do the process, right? Which becomes documenting and, making sure it's followed properly. And so it becomes really burdensome. And the intent of the process is good, but then you get all of this extra stuff that comes along with it, right? So I agree with Annika that there needs to be a process that comfortable with, but then there needs to be flexibility and adaptability in that process. And I think, in straight up teachings, that is lost to some extent, but it's kind of both. And in some cases, yeah, you can throw it away to some extent. If you don't have to guarantee the thing's going to work, then yeah, you can be more flexible. If you have other goals that come out of it, especially with like a capstone, it's more about the learning.
And I think it depends on the mission objective.
Exactly. Yeah.
I mean, just think about it. If you're gonna be sent to space, would you want that a process not be followed? Right? And then the other thing that I want to mention is it depends on the mission, right? If you have a project in school where the whole mission or the whole purpose of a mission, the project, is to give students an opportunity, an experience of a spaceflight mission, right? And simple mission, yes, maybe you skip a few steps. Maybe you're not as disciplined, but still you need to teach your students to be disciplined, to use disciplined engineering methodologies. Okay? And so to me, it's about the mission. It's about whether we're conducting a simple tech demonstration or a science mission, or we're gonna be sending humans to Mars, right? So there's a big spectrum of missions. The other thing that I also want to mention is I've been with NASA for almost 20 years, and I keep hearing, we do paper and paper until PDR. No, it depends on the leadership of the project, right? My teams, we iterate, we prototype, we do a lot of research, a lot of prototyping to get to these critical milestones. So let's not generalize, right? And if you've had the experience of a project manager that does not allow you to do any of that, then to me, that's not very good leadership.
Yeah. We've never had one that hasn't allowed us to. We always follow our good.
I've been very adamant about let's iterate, let's prototype. That's the only way we're going to get to a successful team.
Exactly. Agree.
I think one big factor is the size of your team, because for example, Mars 2020 project that I contribute to for more than a decade, there are thousands of people, and there are not a single person who knows everything. So paperwork, bureaucracy, and process, as much as I hate it, it's an evil necessity. So, but then, echoing what you said, Dean, yes, we have to admit that we need a process, we need some paperwork and bureaucracy, but can we reinvent a process that is more flexible? For example, in the current process, in the planetary mission, you define the science traceability matrix, which you meticulously define all the observations, and then requirements flow down from it. In case of the inside scoop, there wasn't an argument to remove it because it is not in the requirement or not in HTM, right? But eventually, for some flexibility, just stayed in there and it benefited it. So, it's more about how to, reinvent new processes that is more adaptive and flexible.
Well, there's also a big difference when the mission is being developed within the system, right? This is a university, even a company, right? A third party. When our missions fail, no matter how small they are, they make the national news. So I think there's also a little difference. But let's not generalize. I do believe in iterating. I do believe in being agile, right? When it makes sense, right? I do believe that in order to get to a successful PDR, you do have to prototype. That's how you're going to close your design. You can't just close it by paper.
Yeah.
I guess my concern is I've run into those program managers who do only think in terms of the V. And the problem is, I think we need the students to be introduced at least to these different possible processes. Because what I observe is some people get it in their head, there's only one right way to do it, and it's this super formal way. That's kind of my...
To be engineers. This teacher to be disciplined engineers and to know how to use the tools, right? And there's various methodologies, there's various approaches to insist on agree on how you're gonna get it done.
Okay, so my stomach is starting to rumble. So why don't we take one last question if you have any pressing super.
We have to go the entrance 5, so
Okay, so we have to wrap. Sorry about that. I will take that question. All right, thank you guys. Thank you, Annika.
Thank you.